distribution modeling in R. And this is the last step that you take, which is model evaluation. And essentially, I'm just highlighting one of the things that you can do. There's a lot of, and we've highlighted in the other modules steps that you're taking all along the way to evaluate your data, evaluate how your model's performing. So they're all important. And this is just highlighting one example of how to do that. And I think it's important to highlight that EcoCommons, the point and click dashboard, sometimes that will generate the results you need in 15 minutes for the question that you have. So you don't necessarily have to dig into the R environment. But some questions might require a little more investigation. And we've got use cases where the point and click environment has generated the kinds of results you need. But there certainly would be use cases where you need to dig a little bit deeper to get the kinds of results that you need for the question that you're asking. So as EcoCommons continues to grow, I'm hopeful that we will continue to bring on new scientific workflows. And the ones that have been highlighted in this series of videos are just one example. There's a lot of different ways to approach modeling. And hopefully more and more of those will become available on EcoCommons in the future. This is certainly not a comprehensive or exhaustive treatment of species distribution modeling. It's an active area of research. And as always, I want to highlight this beautiful paper that presents one of the best overviews of species distribution modeling and all the different things that you want to think about during the process in one place. And so it's a great paper. Check it out if you haven't already. And so again, we're going to be talking about model evaluation in this module. And I suppose one of the easiest ways to evaluate your model is to look at the mapped predictions. Do they make sense? If you know the species reasonably well, this is a map of Bawden's black cockatoo, glossy black cockatoo. And, you know, these are the areas where there's higher probability that this bird will occur. The blue areas are, we don't think the bird occurs there. Well, at a real coarse level, that map doesn't look terrible, based on what I know. But I might not, I don't live in Southwest WA, so I might pass this map to other experts who have been studying them to get a sense of, you know, is this map producing reasonable results? So that's a quick way to evaluate your model results, but there's all kinds of things that get pumped out if you run your model in the point and click environment. And we've highlighted a lot of these ways to do this in R as well. And we'll highlight some more of them as we go here. But first, evaluate your map by just, are these map predictions plausible? And are there things that might limit the distribution more than is being shown here? And as I talked about in the previous module, generally speaking, we're interested in how well did my model predict the original response variable was presence or absence, zeros or ones. So that's what went into the model. But the output of most of these models is a probability of occurrence scaled between 0 and 1. But generally saying this location has a 70% probability of having suitable habitat for the presence of this species, and the adjacent cell has a slightly higher probability, is not useful to planners and managers and if you want to make accurate predictions of where these species are, you got to choose a threshold and classify all the values above that threshold as being where you expect the species will be present, and all the things below that threshold to be areas where you expect that species to be absent. There are times when it's nice to just give the continuous probability map, but in most instances you're going to want to present a presence-absence map. And when you do that, you can examine, okay, I predicted that there would be no species in this location. And actually, there were no species in that location. But there were some places where I predicted there would be those species, but actually there weren't any. Or I might have predicted there's no species, but there was species. And so this is a true negative where it was actually negative and we predicted there were no species there. If we predicted there were species there and there actually were species there, that's a true positive, right? And then we have false positives and false negatives. And we can do that just based on comparing our predictions at those lat longs with the predictions or with the actual presence-absence data itself, right? So we can generate this thing called a confusion matrix. And most model evaluation draws on those simple 4 values that are generated in a confusion matrix. Now, if we look at AUC, or the area under the curve, generally that's a widely used metric, right? And generally the thinking is if you get an AUC value greater than 0.9, you've got an excellent model. Between 0.7 and 0.9, well, you've got a decent model. But under 0.7, you're not doing much better than random, right? And then there's the true positive rate. So that's looking at the true positives divided by the true positives plus the false negatives and the false positive rate. And it's all taking values from that confusion matrix. If we look at how the false positive rate and the true positive rate vary, so what's the probability of these two things as we increase the threshold? So if we had a perfect model, we would expect this line, when we have 0 false positives and perfect predictions, all true positives, right? This line would extend up to there, and then when the false positive rate is 1, you get this sense that as your thresholds change, this is the curve that should be formed. And this is a random prediction. So if you were randomly predicting true positives and false positives, you'd follow along this line, and you'd have an AUC of 0.5 because this would be your area under the curve. But if you're doing better than that, your area under the curve increases. So that's what AUC is. And I'm going to try and explain that a little bit better. So if we had perfect performance, right? So these are all our true negatives, and they all fall under a threshold of 0.5. And these are all our true positives, and they all fall above our threshold of 0.5. Then our ROC curve, our receiver operator curve, doesn't look like a curve at all. It includes all of this space. The area under the curve is 1. We are predicting perfectly according to our data. But usually, almost always, you have this overlap between true negatives and true positives, where you have some false negatives and you have some false positives. So as your threshold varies, this curve varies and your AUC shrinks. This incidentally is from Toward Better Science, so that's the website where I grabbed this from. It's a great site at explaining some of this stuff. So you get all these metrics of predictive performance when you run a model, and you can get all kinds of different things, right? But if we go back to that confusion matrix, you can have a really unbalanced, you can be doing really well with your true negatives, but you're not doing so well with your true positives. But that might not show up in your AUC, right? So more balanced approaches have been suggested. Possibly the most conservative metric of how well you're predicting is this thing called the true skills statistic, and it really started to get in vogue in the last 4 or 5 years. If you're getting a TSS value that's 0.9 or higher, then you're really doing well. And basically, TSS is just rearranging those values from the confusion matrix in a different way, right? So that's how you get the metric, and TPR is this and TNR is this. So it's just taking different values from that confusion matrix. And this gives more balance to the true positives, right? You have to have a more amount. To get closer to 1, you need to be doing better across both positives and negatives. You get a similar thing with the F1 score, but it's not quite as conservative as TSS. But again, if you're doing better than 0.9, you're doing excellent. You've got an excellent model. Again, TSS of 0.9 or above, and you can start dancing around the room. You can start making some real decisions about what to do on the ground based on those predictions, because that's an excellent result. F1, again, not quite as conservative, but you're doing pretty well. And it's this idea of precision and recall. So what are those things, to get an F1 score? Well, it turns out those things are just bits of the confusion matrix organized in a slightly different way, right? And if you're into maths at all, these will make sense on how they're different. But those are the 3 most common metrics that are used currently. Kappa is another one that takes some information from the confusion matrix and does some other things, other clever things. Also a decent metric to use. If, however, you're using a statistical model, again, and this is an example of, that's the perfect residual plot for a response variable that was not binary. So maybe we were modeling, trying to predict abundance across the landscape. And this suggests that there is no pattern in your residuals, that fairly normal, and a few influential outliers that you might want to investigate. But generally, the assumptions of your statistical model were met. And it's important to evaluate these kinds of results when you're doing species distribution modeling as well. Include those residual plots. So if we're going to evaluate our models just based on how well they predict. So we're either looking to create a really accurate map, or we're looking to transfer our predictions from one spatial location to another spatial location, or from one time to another time, as in the case of climate projections. How are we going to evaluate how well those things are predicting? So ideally, we're going to overlay some independent data on the predictions that we made to see how well the ones and zeros match up with what we predicted would be there, right? So encouragingly, independent data is becoming more and more available. You know, there's growing volumes of acoustic data, which is good for frogs. And so you might get a lot of acoustic data that's coming in from really remote locations where people aren't generally surveying for frogs on the ground. That's a great set of independent data. Camera traps are another thing that's coming online more and more, and telemetry data, movement data is being used more and more. It's becoming more and more available. That's a great way to validate your occurrence predictions. Your data that was based on occurrence data, or your model that was based on occurrence data. But other sources of independent data can be, you know, maybe a team went out and did a whole lot of rigorous surveys, really systematically across a given area that might be smaller than your study area, but still a useful, independently collected data set. That's ideal. But often we don't have independent data to play with. So as I talked about in Module 1, sometimes you're going to want to put some of your data aside, not use it to train your model, to build your model, but just to use it in this validation piece. And then I'm not going to go into cross-validation or bootstrapping. Those are things that are well covered elsewhere. But those are other steps that you can take to get a sense of how well, how sensitive your model results are to the data that's in your data set. So if you have some really influential data points, that'll come out in bootstrapping or cross-validation results. And finally, the worst thing that you can do is simply build a model with training data and not do anything else but generate a confusion matrix from your training data. So you're going to have the least confidence in that result. And generally, you're probably not going to get your model published in the literature if that's all you've done. So you're going to have to go usually up this train, and more you're seeing this almost demanded in the literature. This and this, right? Either partition test data or independent data if it's available. So in this section of the code, I'm not going to cover, there's a lot of code that's written in the scripts. Hopefully you've been through that already. If you have, or if you haven't, I would encourage you to open up that script and annotate it now with notes, just so you can highlight some of the things that hopefully this is clarifying a little bit. But in this section, we're going to show some examples of how to get a threshold to use. And we've already shown some examples of that in previous modules. So these aren't the only ways to do it, but there's a number of ways to generate the threshold. Thresholds are produced in the point and click dashboard as well within the BCCBL modeling wizard in EcoCommons. We'll show you how to generate a confusion matrix, that little magic box with 4 values in it, and how to generate those evaluation statistics based on that confusion matrix. And then we're going to show an example of getting independent data. And unfortunately, these data aren't really that independent. They're also citizen science, mostly ALA records, but they're records that are separate from the frog ID records within ALA. So we'll show you how to use that as an independent data set. And in hindsight, that probably wasn't the best independent data set to use, but nonetheless. And then we're not going to show you how to repeat it all with independent data, but the script is there. So we're going to show you how to do all this with your training data. And then the script is there to show you how to do it with independent data. So the first step, though, we're going to fit another boosted regression tree. And we're going to do that with the Dismo package using the GBM step function. And again, we're gonna drop 2 variables in this model, but in the original model that I ran when I wrote this code, we dropped 2 because we were modeling across all of Eastern Australia. But in order to speed things up, I ran it just in Queensland, and when you run it just in Queensland, the simplify function that we talked about in the previous video in step 3 highlighted that really for the data in Queensland, you probably wouldn't drop any of those variables. You keep them all. But anyway, we fit another model. We're going to create a spatial points layer of the and we've done these spatial points a lot, so I don't spell out all the code, but where the presences are 1 or where the presences are 0, right? So we're generating these spatial points of, where the presences are either 1 or 0. And then we're going to trim down that. This is the stack of environmental predictors, and we're removing those last 2 variables. Again, we didn't need to do that in Queensland, but we did for Eastern Australia, so that's still in the code. And then we're going to predict using this model object and using some new predictors, which are these, the LIPE predictors. And let's see, then we're going to do something new. So Dismo also has something called an evaluate function. So what it's going to do is it's going to take those presences and absences in the training data and look at how they compare to the data that's in that model object. So and inclusive of the new predictors, that new stack of predictors. And using that, so it's a new model object, which is called BRT eval training. And using that, there's all kinds of rich stuff in that model object, including you can just pull out the optimal threshold based on maximizing your kappa value, or you can pull out the optimal threshold based on maximizing species sensitivity, or you can use a variety of stats here and generate the optimal threshold based on that evaluation model object. And based on that new threshold, so say that we're going to use kappa, we're going to do that reclassify again. So we've done this a lot now, where we create a matrix where everything between -5 and the threshold that we've set is going to be set to 0, and everything between that threshold and 2.1 is going to be set to 1. And we're going to reclassify that and plot it. And so when we plot that, we see this is what we get. So we still have some points that are falling in areas where we didn't predict this frog would occur, but a lot of the points are falling in areas where we did predict this would occur, this frog. And then we kind of want to see, okay, how well did that training data actually predict? So what are the values on this map for each of those points? So what we're going to do yet again is we're going to create a spatial points layer from the lats and the longs that were used in the training data. And then we're going to extract either a 1 or a 0 in this thresholded map. So this map is either 0s or 1s in the shaded areas, and it's going to extract those 0s and 1s. And then the next step is to create a data frame that has basically 2 columns. One is the original presence-absence locations, the 0s and the 1s. The other one is what we predicted based on this map, on this previous map here, right? We extracted those 0s and 1s from here. So we've got a column of the reference values, which are the actual values. In our case, pseudo-absence values, so not, but those are what we used as 0s and 1s in our training data. And what was the predicted value based on the threshold of maximizing kappa? Was there a 0 or a 1 in each one of those locations? And here we're changing these 2 columns to factors, and we're changing the order of them. And we're doing that just so this next little function works. And this is just a handy function. So you could go through and create a confusion matrix. Where were the values actually 1 where I predicted they were 1? Where were the values 0 where I predicted they were 1, right? Or where were they predicted to be 0 and they actually were 0, right? You could do that in a variety of ways. This just saves a bit of time, this little function, confusion matrix, and this formats your data so that confusion matrix function works. And we're going to use those 2 columns within the data frame, the predicted and the reference, to generate a confusion matrix. And this is what pops out. That's all. There's actually other things that come out of this as well. But the confusion matrix is the confusion matrix table. There's other things in this model object that you can check out. But essentially, this is how well we performed. And, you know, we had a fair number of, we didn't do too poorly. And then we take these values, each one of these values. So true positives are here, the 1s and the 1s in this particular matrix, right? And so we predicted it was there and it was actually there. So all this is doing is, this line of code is returning this value of 792. This one is returning the value of 255. This one is returning the value of 158. And this is TN is returning the value of 375. And then we're calculating the false positive rate, the true negative rate, using those numbers. So it looks like a lot of code, but all it's doing is taking those 4 numbers out and then rearranging them. And we do that for TSS, we do that for the F1 statistic, and we can do that for the training data. And what's interesting And I need to check the code that this is actually right, or I didn't do something silly. But the independent data, we get the same values. And in order to do this on the independent data, so I haven't included all the code, but we need to download all the ALA records that aren't frog ID records. We need to take the same process of generating the presences and the absences that we did in the step 1 video. And we then need to predict using those new locations. So not only the environmental data, but we're going to predict using those new locations, and we're going to see how well independent data predicts into overlays onto the these areas. So essentially, we're just going to take the independent data and we're going to extract. Okay, the independent data says this is a 0 or 1. What did my model predict as being there? Did my model predict a 0 or a 1? So we're not running a new model, right? We're just pulling the zeros and ones out from another data set that has zeros and ones. And again, I don't go through all that code because it's just repeating processes that were either in step 1 or earlier in step 4. But here, and again, I need to double check these values. If I didn't, I might have done something silly in the code to get the same results. But if not, it wouldn't be a surprise to get similar results because it's all citizen science data within ALA. We've got a lot of records to drive the model. We've got the same variables that were used. I mean, it wouldn't be shocking to see that this data set performed very similarly to the other one. And certainly when I ran this initially for all of Eastern Australia, the independent data, the F1 score was a bit lower and the TSS score was very similar, similarly low. But there was a drop in the F1 statistic. So why we're getting this result, we'll have to investigate that a little bit further. But essentially, if you get a big drop with the independent data, that means you've overfit your model, right? Here we're getting scores that are suggesting we're not doing great. We're doing better than random, maybe a bit better than random, but these are not great results in terms of the overall model. But it's fairly stable. So we would get similar results with different data from ALA at least. Other things to consider when we're evaluating the model. Okay, we've got these response curves. So does it make sense that my probability of occurrence on the y-axis is changing like this as this environmental variable changes? Or is this nonsense? If it's nonsense, your predictions are probably nonsense and they're probably not going to predict well into new environments or across time. Similarly, if your map looks like junk, it probably is, right? But this looks interesting. This looks like investigating it further. And then, well, hang on, this is the results we got from the Maxent model. Well, we could take those results and apply a threshold, which we've done here, and evaluate how those ones and zeros line up. The predicted ones and zeros line up with the actual ones and zeros, right? And then we can see, well, we got a better F1 statistic with BRT than we did with Maxent. We might go with BRT. So that's one way to evaluate your model performance between different models, but sometimes the differences are very subtle, right? There's not huge differences. ecologically or biologically you can't think of any reason that one would be performing better than another one. When that's the case, when you really can't choose between some of the statistical model results that you're getting and some of the machine learning results that you're getting, and you don't have a real clear reason to use one or the other. And often for many questions, you will prefer one of these methods over the others. But if you don't have that understanding of why one method would be better a priori before you go into it, then averaging those model results, taking an ensemble model approach, works pretty well. And this paper that came out recently highlights that it works better than most. But if you're an expert in boosted regression trees like Jane Elith is, and you can do some tuning of your boosted regression trees, you can actually get a better result, fine tuning that model than you can with just an overall average. And that's probably true with other models. So statistical models, if your response variable, for example, is highly zero inflated, you might do better with a GLM that's addressing that zero inflation issue than you will with some of these other methods. So those are open questions, yet to be proven in the literature, but certainly in my experience, I've seen a bit of that. And again, so you can average results. If you don't get clear differences from your evaluation statistics between methods, between models that make sense, then averaging them, it probably isn't a bad way to go. But sometimes you'll get a clear winner when you do these evaluation statistics between models. Sometimes it'll be very clear which one's best. Or other times it'll be very clear which one's best based on your understanding of the way the model works and your available data. So again, you want to roll back to this. Did your data at the end of the day match your question? Maybe the resolution of your data was too coarse to do what you wanted to do. Maybe your occurrence data, really you thought it was more structured, but really it was pretty unstructured at the end of the day. And there was a lot of uncertainty in it. And there was a lot of variation in how well your environmental space was sampled or how well your geographic space was sampled. So while we have predictions across these areas, both geographic space and environmental space are poorly represented in this part of the region where we're making predictions, for example. So you want to keep those kinds of things in mind. In short, there's no one statistic that you can go to and say, I've evaluated my model. You have to look at as much of it as possible and assess it against the question that you've asked, right? So sometimes different evaluation metrics are more important for some models than others. And again, once you have a result, just keep in mind that you want to pass that result on to an audience in a way that isn't going to undermine the credibility of your modeling. If you modeled at a regional or nearly geographic scale, and that looks like a pretty decent result at that scale, it tells you that there's none of these birds out west or way up north, but you give results that are highly precise like this, you might lose some credibility if people know these local areas where you've predicted there are birds and there aren't any there, and they know that. So just give the results to an audience that's prepared to use them in the way that the results were intended. And that wraps it up. So at the end of the day, model evaluation isn't that complex, and the confusion matrix is the most common way that it's tackled, or residual plots for statistics. If you need to learn more about R, to understand, some of what this code is doing, I'd really encourage you to get your basics down pat, and you can do that by visiting this website and going through their tutorials. You can then listen to the educational videos that walk you through those materials, given by Amelia, who's on our team. There's a lot of other educational materials available, right? So there's a lot of other things you can do in modeling, and my approach isn't the one-size-fits-all approach. There's a lot of other examples that we'll be bringing online, use cases that show how you can use these tools. So we'd encourage you to give us feedback. If you have questions about things, just get in touch with us. We're more than happy to talk to people about modeling and the tools that are available on EcoCommons. And if you're interested in what we're doing, please visit our website, follow our journey, sign up for our newsletter. And finally, just want to thank all the people that make the work that we do possible. It's not possible without data. It's not possible with really rigorously vetted scientific workflows. It's not possible without the digital infrastructure that lets us do all this on the cloud. Amazing advances. And hopefully, the tools that we've talked about today will make your life a little easier. Again, some of the things that you might want to do, you might be able to do all of that within the point-and-click dashboards. This is just some examples of some other steps that you might play around with while you're modeling your question. Anyway, thank you if you've made it this long, I'm impressed. So thank you for tuning in, and please send through any feedback.